Thank you, Dan, for the introduction. Hi, everyone. It's my pleasure to be here and present our work on precise data center traffic engineering. This work is done with my collaborators from Google and AirBNB and my advisors, Srini and Peter. So if you've never been to a data center, you probably have seen something very similar like this. This is how a data center would look like. There are racks after racks on the floor, and then network wires running on the top. And of course, there's always some fancy blue light as well. But for the rest of the talk, I'm going to simplify the topology a little bit and draw it like this. So the machines and level 1 switch in the dashed circle, they map to a rack in the photo. And then there are also network links connecting machine to switch and switch to switch. These network links can be heterogeneous and have very different capacity. So data center network is, of course, massive in scale. And there are many paths between the end hosts. Each pair of end hosts may want to send some amount of data, which we refer to as demands. So it is important to figure out how to route these demands while achieving optimal load balancing or maximum throughput. And for that, we need traffic engineering. In a typical T system, the T control loop consists of 3 steps. First of all, the end host demands will be collected and sent to a T controller. The T controller runs some optimization algorithm in order to figure out the optimal way to route these demands. And because it's a large and complex problem, the algorithm usually runs on a powerful platform. And the finding is called the T solution. The T solution will be sent back to the switches. The switches need to implement the T solution based on the spec. So taking the red pair, for example, the T solution specifies that this demand should be split as 39G and 15G across 2 ports. And switch T1 needs to implement this requested traffic distribution in its memory. This entire T control loop repeatedly runs every other minute to quickly adapt to the changing network conditions. So we need to make sure that all the steps in this control loop are running fast. And our focus is to make sure that the switch can implement the T solution. Regarding how the T controller comes up with the T solution, it's a different topic that we're not going into. And continuing on the previous example, now let's take a closer look at switch T1 to understand the T implementation. So there are 2 sets of rules in the switch memory, destinations and groups. A destination rule matches on the longest prefix of destination addresses. It then points to a corresponding group that tells the packet where to go. So basically, when a packet comes in, it's going to hit one of the groups. And a group here is basically a data structure that contains a set of egress ports. So the packet will uniformly select an egress port at random and then go there. For packets going to the red destination, as you see in the figure, they'll fall into the G1 bucket. And to approximate the desired traffic distribution, ports P1 and P2 will be replicated 39 and 15 times each. But here's a problem. These switches have very limited memory. And on the other hand, entry replication like this will usually take up a very large chunk of space. So in other words, the groups cannot fit into the switch memory. Let's say in this example, we only have memory space for 10 port entries. Okay? And so we really need to make the group size smaller. We can do something like this. 13 to 5 is strictly equivalent to the original ratio. But it still exceeds the memory limit. Or we can tweak the weights and round them to, say, 3 to 1. This is cool because now G1 only consumes 4 entries in total. So that fits into the limit. And the process of reducing a set of original groups to a final smaller version is called group reduction. This is usually handled by some group reduction algorithm that's running alongside the T controller. And it's also important to point out that the final group of 3 to 1 will actually change the intended traffic distribution to 41G and 13G in this example. And this creates a difference between the T solution and the T implementation, which we refer to as precision loss. So this is an important concept. What I have talked about is just the impact of precision loss on a single switch. Actually, precision loss can also affect the network as a whole. So we have seen the traffic imbalance in this example, but now let's denote the imbalance in a simpler form. So plus 2G here means that link is carrying 2G more traffic than expected. And imagine the network has more tiers. Now switch S1 will receive more traffic than expected, but it can also contribute to actual imbalance. Let's say 1G of extra traffic going to the right link. So switch R2 in the next tier will get 3G more traffic. And this can happen again in the next tier and so on and so forth. So precision loss just accumulates higher and higher for the downstream switches. Precision loss sounds bad, but why should we care? The imbalance and congestion it causes has a negative impact on flow completion time. We collected measurements from a Google production data center network, and what we found is that the tail flow completion time can go up by 40% if the link utilization increases only by 10% as a result of load imbalance. So it is always desirable to have lower link utilization, but reality will say otherwise. This figure shows the CDF of link utilization in this Google network. And the blue curve represents an ideal scenario when the group weights are implemented precisely, so there's no precision loss at all. And then the red curve here is the actual link utilization measured from this network. As you can see, there is a long tail of high link utilization. That's about 15% of the total links. And if we look at the worst case, the actual link utilization can be up to 5 times higher than the ideal case. In addition, we also observed congestion loss on the worst few links. So we know precision loss is due to limited hardware resources, but why is it so bad? Turns out there are 5 root causes. But first of all, let me remind you that the grouped space usage depends on 3 factors: the number of groups, the number of ports per group, and port weights. So let's use this diagram to explain what the root causes are. Number 1 is scale. So as the network gets larger, the number of groups also increases. Number 2 is path diversity. So this means the number of ports in a group. And TE sometimes would use many ports in a group for good reasons, but that also makes the group size larger. And root cause 3 is skewed weights. As you can see in this example, GN, the weights can sometimes be very skewed. And because the weight 1 is already the minimum integer, we cannot reduce it any further. So to make this group smaller, we have to reduce weight 99. But the more we reduce that weight, the more precision loss will occur. And root cause 4 is heterogeneity. Recall that all of these groups have to be installed on a switch. And in production, we have a mix of old generation and new generation switches. The old generation switches can have 8 times less memory space than the new generation. So which means the groups will be harder to fit in. But then on the other hand, the mixed speeds of these switches also mean that it's going to cause larger weights in groups because the higher speeds means more capacity for more traffic to fit in. And the last root cause is the cascading effect. Recall from the previous example where we see that precision loss can propagate and accumulate in downstream switches. In fact, precision loss can get amplified multiplicatively in a hierarchical multi-tier network. So that is what I mean by the cascading effect. And to recap, what we've learned from the 5 root causes is that we need to optimize both the per group size and the total group size on the switch. The natural question to ask is, how is it done today and what is wrong? The group reduction algorithm used by Google today is called table fitting. Table fitting can be inadequate in certain scenarios, which we'll see in evaluation. So this is exactly why we're trying to come up with new algorithms. But also note that these issues that table fitting has are also opportunities for us to improve on. The first opportunity is that groups can become identical after reduction. Identical here means all of the ports on the two groups and the weights associated with each group, with each port are identical. And the second opportunity is that different groups can contribute to the overall precision loss differently. The last one is that all of the reduction algorithms today try to preserve all of the unique ports in a group, even though that might not be necessary. So all of these opportunities lead to three heuristics that we propose. One is called group sharing. The idea is because groups can become identical after reduction, it makes sense to deduplicate them and reuse just one. And the next heuristic is called table carving. So different groups can serve different amount of traffic, and it is unreasonable for a group that's serving only a tiny fraction of traffic to take up a large chunk of space. So the idea of table carving is to allocate space to each group proportional to its traffic volume. And the last heuristic is called table pruning. When necessary, table pruning will give up on the port preservation property and prune select ports from the group to further reduce the group size. So group sharing would mitigate the scale and heterogeneity challenges by making efficient use of the available space. Table carving and group pruning both will address the path diversity and skew weights challenges by limiting the impact of individual groups. And all these three heuristics combined will address the cascading effect by minimizing the per tier precision loss. Next, let me introduce two new group reduction algorithms built on the three heuristics that we just saw. They're called DMIR and IGR. They both aim to convert a set of given groups to a smaller version. DMIR's core algorithm is mixed integer programming, and IGR is based on greedy search. Due to the nature of mixed integer optimization, DMIR can find more optimal solutions, but it also runs slower than IGR. To understand how these two algorithms work, let's look at a small example. So we have three groups to reduce, and the size of each group basically represents the original space it's going to take. And then we also have a chunk of available space. On top of that, we know the traffic volume that each group is carrying. So step one of the algorithm would invoke table carving. The available space will be allocated proportional to each group's traffic volume, like this. And then step two, each group will be reduced individually in parallel. And here, DMIR and IGR would call their own core algorithm to do the job, but both would invoke the group pruning heuristic. When this is done, the groups should be reduced to a version that can fit into their allocations, and we name the outcomes G1 prime, G2 prime, and G3 prime. At this point, we might realize that G1 prime and G2 prime become identical. So step three of the algorithm would invoke group sharing. So we deduplicate G1 prime and G2 prime. This is what the final result would look like. Finally, I'd like to show you some results for evaluation. We report data on a network level metric, link utilization, and an application level metric, flow completion time. This figure is a bar chart of link utilization. So it has P50, P99, and max on the x-axis. So that covers both the common case and tail link utilization. We compare with the current approach, table fitting. And DMIR and IGR both do a pretty good job keeping the link utilization close to the ideal scenario. If you look at the worst case, table fitting can see up to 67% error compared to the ideal scenario. But DMIR and IGR only see 7% error compared to ideal. On the other hand, if we look at the application impact, so the right-hand side figure will show that. It's in the same network setting, same network scenario, and we again compare with table fitting. DMIR and IGR kind of fall in between, and if you look at the worst case, table fitting can see up to 1.6 times longer flow completion time, whereas DMIR and IGR only see 1.2x longer flow completion time. And of course, this is just one example. DMIR can outperform IGR in certain challenging scenarios. Please see our paper for more details. Precision loss is not everything. We also care about the speed of these algorithms because recall that we said the T control loop runs every other minute, so they really need to be fast. And therefore, we compare the average time to reduce the batch of groups on the switch. And the group reduction time is measured under a range of scenarios. Without telling you what they are, I will just say that they cover a range of common to rare scenarios. And the time is presented in log scale. I'm not showing the ideal bar here because ideally group reduction time should just be 0. You can see that IGR outperforms table fitting by 1 to 2 orders of magnitude, and DMIR is on par with table fitting. To summarize, precision loss is an inherent problem in traffic engineering, and we have designed 2 group reduction algorithms to do the job. When comparing with the current approach, they can reduce precision loss by 10x and FCT by 26%. They also run up to 10x faster. And in terms of when to use which, we recommend IGR for responsiveness and DMIR for the challenging scenarios. You can also scan the QR code here and check out this project online. Thank you for your attention. With that, I'm happy to take questions.